All right, let's dive in. Today, we're jumping into what I think is one of the coolest and most powerful areas in all of AI, reinforcement learning. It's basically the science of how a machine can teach itself to do some pretty amazing things.
But have you ever really stopped to wonder about that? I mean, how does a machine learn to win a complex game, or figure out a maze, or heck, even learn all the steps to make breakfast, completely on its own? We're not talking about giving it a list of instructions. We're talking about it learning from scratch, from pure experience. And that's the central puzzle that reinforcement learning is all about. So, when you boil it all down, it's really about learning by doing. You have what we call an agent. That's our learner. It takes an action out in the world or its environment. It sees what happens, and then it gets feedback, a reward, or a penalty. It's this continuous loop of trial and error, all driven by a single, simple goal: get as much reward as you possibly can. Okay, so here's our game plan. First, we'll look at how this whole idea of learning from consequences works. Then, we'll get into the really tough puzzles that RL has to solve. After that, we're going to peek inside the agent's mind to see how it thinks. And finally, we'll see how all this theory helps an agent go from simple mazes to, well, becoming a kind of mastermind. So, first things first. Before we go any deeper, we need to figure out where reinforcement learning fits into the bigger AI family tree. Because, its whole approach to learning is really, really different from its relatives. You've probably seen charts like this before. Generally, we split machine learning into three big camps. You've got supervised learning, which is all about learning from data that already has the answers. Then there's unsupervised learning, which is great at finding hidden patterns. And then there's our focus for today, reinforcement learning, which is in a league of its own because it learns by interacting with the world. And here's the real kicker, the thing that makes it so different. Think of it this way. Supervised learning is like a student studying for a test with a complete answer key. For every single question, it's told exactly what the right answer is. But a reinforcement learning agent, it's more like a scientist in a lab. It has to run experiments, see what happens, and figure out the answers all by itself. No answer key provided. So you might be asking, why do we even need this whole separate branch of machine learning? Well, it's because RL is specifically built to solve these really tricky real-world problems that other methods just can't. Let's look at the kinds of puzzles it's designed to crack. You see, at the very heart of reinforcement learning are these four huge challenges. First is optimization. That's like trying to find the absolute best path to the top of a mountain. Then you have to deal with delayed consequences, which is like planting a seed today and not seeing the fruit for a long, long time. Third is exploration, deciding which new paths are even worth trying. And last is generalization, which is all about taking what you learned in one situation and applying it to a brand new one.
Okay, this one is huge. And you know this from your own life, right? Think about deciding what to study in college. That one choice you make today could have a massive impact on your career, but you won't know for sure for years. Well, RL agents face that same exact problem. How on earth do you connect a great outcome to a specific action you took way, way back in the past?
The classic dilemma. Do you go to your favorite restaurant because you know it's going to be good? That's what we call exploration. Or do you take a chance on that new place that just opened up? It might be amazing, or it could be a total bust. That's exploration. And every RL agent is constantly trying to strike the right balance between these two. And this slide just nails that whole dilemma. Look at our little robot here. It can play it safe, move to the square on the right, and grab a guaranteed, easy reward of +3. That's exploitation. But what about all those other squares it hasn't seen yet? It could explore and find a treasure chest worth a whopping +10, or it could stumble into a trap and get a nasty -10 penalty. What do you do? That question is the very essence of this puzzle. Okay, so we've laid out all these tough puzzles that RL is built to solve. So now for the really cool part. How does it actually do it? What's going on inside that agent's quote-unquote mind? Let's open up the hood and look at the essential tools it uses to think. Turns out, every RL agent is basically built from a few key components. It's got a policy, which is its current strategy. It has a reward signal, which defines its ultimate goal. It has a value function, which gives it a sense of foresight. And sometimes it even has a model, which is like its own internal map of how the world works. So the policy is pretty much the agent's brain. It's the rule book it follows. It just maps the situation to an action. Simple as that. When the agent sees this, the policy says do that. And the entire goal of all this learning is to figure out the best possible policy. The reward signal is way more straightforward. It's just that immediate feedback from the world, a single number that basically says, good job, with a positive score, or nope, bad move with a -1. The agent's entire reason for being is to rack up the highest total reward score it can over its lifetime. Now, this is where it gets really clever. The value function is totally different from that immediate reward. This is all about foresight. The value of a situation is its potential for total future reward. An action might give you a tiny reward right now, but if it puts you on a path to collect huge rewards later on, then that situation has a very, very high value. And this quote just illustrates the difference perfectly. Think of it like this. Eating a candy bar gives you an immediate reward, right? A little hit of pleasure. But choosing to eat a healthy salad, well, that has a much higher value for your long-term health. Rewards are for now, values are for the long game. We've been pretty deep in the theory, which is great, but this is where the rubber meets the road. Let's connect all these ideas to some actual concrete examples. I think you'll be surprised to see just how common these principles are. I mean, just think about something you probably did this morning, making breakfast. It seems so simple. You don't even think about it. But if you actually break it down, it is an incredibly complex dance of decisions and little sub-goals. Every single step, walking, opening, selecting, grasping, is an action guided by the ultimate goal of getting some food. It's a perfect everyday example of a reinforcement learning problem. And once you start looking for it, you realize this framework is literally everywhere. A chess master is thinking about the long-term value of a board position, not just capturing one piece. A brand new gazelle learns to run through frantic trial and error, getting a painful negative reward every time it falls. And high-tech systems, from factory controllers to cleaning robots, are constantly taking actions to maximize some goal, whether that's efficiency or just finding the charging dock. So let's bring it all back together. If you look at this chart, you see that all kinds of machine learning learn from experience in some way. But the two things that really make reinforcement learning stand out, its special skills, are dealing with delayed consequences and the absolute need for active exploration. That's its superpower. So in the end, you have to realize that reinforcement learning isn't just a single algorithm. It's a whole framework. It's the problem of learning from interaction. It's the huge family of methods we've designed to solve that problem. And it's the entire scientific field dedicated to pushing this amazing idea forward. And that leaves us with a pretty mind-bending question, doesn't it? If a machine can teach itself to master a game like Go, or a robot can figure out how to make breakfast, what comes next? What are the really complex, really important decisions we're going to ask these systems to learn in the future? The possibilities are just incredible to think about. Thanks so much for joining me today.